have here another solution for an indeterminate beam. So using method of consistent deformation for beams. So this time we'll be having two redundants. Okay, so we will be having two redundants if ever the beam is indeterminate to second degree. So let's say we have this given beam. So first we have to check the degree of indeterminacy. So I is equal to reaction minus equation minus condition. Okay, so for this beam, so we have a fixed support here. So 1, 2, 3 reactions at the fixed support, 1 at the roller, and another at the roller. So 3 plus 1 plus 1, so we have a total of 5. So 5 reactions, we have minus 3 equations of equilibrium. Then we don't have any internal hinge on the beam, so we don't have conditions, so that would be 0. So therefore 5 minus 3, that would be 2. Second degree indeterminate. Okay, so of course for second degree indeterminate, we cannot solve the reactions of this beam by statics alone. So we have to generate two compatibility equations to be able to solve for the reactions, or that is the two redundants. So for this beam, what are the possible redundants that we can consider? So we can consider the MA as redundant. So we have the RA, the RB, or the RD. Okay, so we can choose two of these reactions to be redundant. So for my solution, I'll be considering MA and say RB as my redundants. Okay, so this would be my redundants that I'll be using for my solution. Okay, first is we have to write the primary structure. Okay, primary structure. Okay, for the primary structure, so since I considered MA as redundant, so this will become, so I will remove MA, so there will be no moment, so that will make this as pin. Okay, so this will become pin. RB is another redundant, so I'll be removing the roller, and the roller there will remain the same. Then copy the loads. Okay, so this would now be our primary structure. Okay, so this is 5 meters, 2.5, 2.5, and this is 1. So as you can see, our primary structure becomes determinate already. So we'll have the reaction, say AY, and reaction here, say DY. Okay, so let us solve for the reactions. So if I sum moment at A, what would be the reaction at DY? Okay, so that would be 25 times 5 times 2.5 plus 50 times the moment arm is 7.5 plus another 50 times the moment arm is 11. Okay, divided by the distance of dy divided by 10. So our dy would be 495 over 4. Okay, or 123.75. Okay, so if we sum up forces vertical, I could solve for AY, and that would be minus 25 times 5 plus 50 plus 50. Sorry, 25 times 5 plus 100 minus the reaction at D, 495 over 4. So the reaction here is 405 over 4, or simply 101.25. Okay, now next is to draw the two redundants. Okay, say redundant structure, say for MA. So what would be the redundant structure due to MA? So just copy the beam. Okay, so hinge, then you have roller there, and I'll be putting back MA. Okay, MA is a counterclockwise there. Okay, so this would be 10 meters, and this is 1 meter. Okay, but I don't know MA, so I will relate it with a unit load. What? 1 kilonewton. Okay, so 10, and this is 1 meter. Then we will also solve or consider another redundant structure. This time this is based on the second redundant RB. Okay, RB. So for RB, so I'll be putting back RB. So there, where RB. So this is 5, this is 5, and this is 1. Okay, so but we don't know RB, so I could relate this to a unit load. This is unit moment. This time this would be a unit load, kilonewton. 5, 5, roller, and this is 1. Okay, now, so from the primary structure, due to the actual load, the beam or the elastic curve of the beam would be something like this. Okay, so considering RB, so for this case, the beam width will deflect like this. Okay, so if I'll call this as delta B due to the original load, I will call this as delta B due to the redundant RB or BY. Okay, so this would be FBB. Okay, now so likewise, due to the redundant MA, due to the counterclockwise, so the beam will deflect like this. Likewise here also. Okay, so the deflection over here, the deflection here would be delta at B due to the unit load at moment at A. This is F, B, A. Okay, now what about for, so considering deflections, as we all know that the deflection here, so for the compatibility equations, compatibility conditions, okay, so we know that delta B would be equal to 0, right? Because there is a roller in the original beam. So that means this delta BO, the sum of this plus this BA, then plus this delta BB should be equal to 0. Okay, now but what is delta BA and delta BB? Okay, so I could relate this to, due to 1 kilonewton, okay, and this one also I could relate this one, 1 is to RB as FBB is to delta BB. So therefore I could say that 1 times delta BB is equal to RB times F BB. So that's delta BB. Okay, so for this one naman, we have 1 kilonewton meter is to MA as to FBA is to delta BA. So I could say that 1 times delta BA cross multiplication is equal to MA FBA. Okay? So substituting this delta BA, so this becomes delta BO plus delta BA is this MA FBA there, then delta BB is here, that is RB plus RB times FBB equal to 0. So this would be our first compatibility equation relating MA and RB. So we have to generate another compatibility equation relating MA and RBB. So how? So then the next, considering the next redundant. So the first compatibility equation was formulated based from the redundant on delta B. Now what about MA? So MA, so that's the moment at A. So as you can see from the primary structure, if I'll draw a tangent line at A, so I will have this theta at A due to the original load, theta AO. Okay? But due to the redundant here, this will create this deflection or slope, and this would be delta at A due to moment at A. So this is FAA. While for this one, this would be the slope at A due to the redundant B. While this one, this is the slope at A due to the redundant at B. Okay, so small f A due to redundant at B. Okay, so we could relate these two. How? So we could do the same relationship. Let's say 1 kilonewton meter is to MA as to FAA is to theta AA. So therefore I could say that 1 times theta AA cross multiplication is equal to MA times FAA. Okay, so cross multiplication lang dito. Likewise for this case, I could relate these two from 1 kip is to RB as to FAB is to theta AB. Okay, so I could rewrite this as 1 times theta AB is equal to RB times FAB. Okay, so what can you say about the theta at A from the original beam? Since this is a fixed support, we know that theta A is equal to 0 for fixed support. So therefore, the summation of this plus this should be 0. So that's theta AO, theta AO plus theta AA plus theta AB should be equal to 0. But what is theta AA? Theta AA is equal to this. So substituting, so theta AO is equal to theta AA is this one. So we have MA FAA, that one, plus theta AB. Theta AB is this one. So we have RB times FAB. Should be equal to 0. So this is my first equation. This would be our second equation of compatibility. So as you can see, we have two equations with two unknowns. The two unknowns are MA and RB. Okay, so by solving simultaneous equations from these compatibility equations, we could solve for that MA and RB. But the big question is, how do we solve for these deltas and thetas? Okay, so since the primary structure as well as the redundant structures are all determinate, so we could solve for those deltas and thetas. Okay, so let us solve it one by one. So first, okay, so these are the equations involved, the compatibility conditions. So we have two equations with two unknowns, MA and RB. So we will solve for the deltas and the thetas this time. Okay, first, considering the primary structure. Okay, so we have this primary structure. So here. Okay, so we have a simple with uniform load of 25, then 50 and 50 here. Okay, so this is 5, 2.5, 2.5, and this is 1. Okay, so to solve for delta BO and theta AO based from the original our primary structure, we could solve this using any of the classical method. So this time I'm going to use, say, using double integration method. Okay, so for double integration method, so I will consider this as my origin, and this would be the range of my x. So my x would be coming from here 0 up to an x equal to 11. Okay, so let me write the equations. So let's say EI y double prime is the moment equation. So if we cut the section or the beam here and I consider the right segment, so if I'm considering the right segment, so by my sign convention would be clockwise negative, counterclockwise would be positive. Okay, so let's say first we have to solve for the reactions first. So we need the reaction here and the reaction there. So this is the reaction at point D. Okay, and we have solved it as 495 over 4. There, 495. 495 over 4 is actually 123.75. And that 405 divided by 4 is actually 101.25. So these are the reactions based from the actual loadings. Okay, so writing the moment equation, so cutting sections here, I'll have 50, that is clockwise, so that is negative. Negative 50 times x. Then we have this one, that is counterclockwise, so that's positive. 123.75, and the moment arm of this from this point is x minus 1. So x minus 1. Then we have another 50, so that's negative 50, and the moment arm is x minus 3.5. X minus 3.5. Then the uniform load is clockwise, so that would be another negative, and the uniform load is 25 times x minus 6, x minus 6. Okay, so x minus 6 is this one. Then the moment arm would be x minus 6 also over 2, so that would be square over 2. So that would be my moment equation. So integrating it once, ei y prime, so that would be negative 50x square over 2. Okay, then plus 123.75 x minus 1 square over 2 minus 50 x minus 3.5 square over 2 minus 25 x minus 6 cube over 6 plus the first constant of integration. Okay, then while the EIY or the deflection equation will be negative 25 x cubed over 3 plus 123.75 x minus 1 cube over 6 minus, we have 25 x minus 3.5 cube over 3 minus 25 x minus 6 to the fourth over 24 plus c1 of x plus the second constant of integration. Okay, now, so what we are looking at are the values of delta BO and delta theta AO. Okay, first is we have to evaluate the constants of integrations. So, what are the boundary conditions? Okay, so from this beam, we know that origin at this point, so at x equals 1, okay, at x equals 1, the deflection there is 0 because that's a roller. Okay, so substituting this boundary condition on this deflection equation, so it gives us 0 is equal to x is 1, so that would be negative 25 over 3. Then if x is 1, this would be 0, this would be negative, so forget about this. This would be negative, forget about this. So we'll have plus c1 of x is 1 plus c2. Okay, so this would be my first equation. So I cannot solve for c1 and c2 because I just have only one equation. The second boundary condition would be at x equals at this point. So at this point, x is equal to 11. Okay, so x is equal to 11. The deflection there is also 0 because that is a hinge support. Okay, so substituting this boundary condition in this equation, deflection equation, that gives us, say, 0 is equal to 11. So that would be negative 25 over 3 times 11 cube plus 123.75. 11 minus 1 is 10 cube over 6. Then here is negative 25 over 3. 11 minus 3.5 is 7.5. 7.5 cube minus this one is 25 over 24. 11 minus 6 is 5. 5 to the fourth plus C1 times 11 plus C2. Okay, so simplifying this one, so this would be 0 equals